Strategic leap, Polaris Spaceplanes to develop hypersonic transport solutions under €50 million defense contract. Date, March 1, 2025. Overview. In a landmark achievement for hypersonic technology, Polaris Spaceplanes, an aerospace startup based in Bremen, has secured a substantial contract from Germany's Federal Office of Bundeswehr Equipment Information Technology and In-Service Support BAAINBw. The contract, valued at approximately €50 million, directs Polaris to design a fully reusable hypersonic research vehicle named AURORA. This initiative is expected to propel advancements in both defense capabilities and scientific research. Company background. Founded in 2019 as a spin-off from the German aerospace center DLR, Polaris Spaceplanes has made significant strides in aerospace innovation. The company has focused on developing multipurpose spaceplane technology, with AURORA being its most ambitious project to date. Prior to this, Polaris successfully developed smaller demonstrators MIRA II and MIRA III, 5-meter-long vehicles that have collectively completed over 100 test flights. This foundation of experience positions Polaris to tackle the complexities of hypersonic flight. Contract acquisition. On February 27, 2025, Polaris announced the acquisition of the BAAINBw contract, which encompasses not only the design phase of the AURORA vehicle but also options for its manufacturing and subsequent flight testing. This contract follows Polaris's earlier contract in April 2023, which focused on the development of a linear aerospike rocket engine, a technology that is integral to the performance of hypersonic vehicles. Vehicle specifications. The AURORA hypersonic vehicle is designed to be approximately 28 meters in length and will function as both a conventional aircraft and a rocket. It is engineered for horizontal takeoff and landing and is capable of delivering payloads of up to 1 ton into low Earth orbit. The vehicle serves as a testbed for advanced research in high-speed flight aerodynamics and propulsion technology. This dual-purpose design will not only enhance military capabilities but also enable scientific exploration and commercial satellite launches. Technical innovations. A significant aspect of the AURORA project is its use of advanced aerospike rocket engines. Aerospikes have historically presented engineering challenges but offer superior efficiency across various altitudes. Polaris is addressing these challenges through the development of innovative cooling technologies and advanced materials. The company has already achieved a notable milestone by conducting the first-ever flight powered by an aerospike engine in October 2024, demonstrating the feasibility of this technology for hypersonic applications. Future prospects. The design phase for AURORA is expected to be completed within 3 years. Following the design phase, the vehicle could also be adapted for use as a small satellite launch system by incorporating an expendable upper stage. This adaptability underscores the potential of the AURORA project to not only meet military needs but also contribute to commercial space ventures, thereby expanding its operational scope. Implications for defense and research. The BAAINBw contract signifies Germany's commitment to bolstering its hypersonic capabilities amid growing global competition in aerospace technologies. As countries increasingly invest in hypersonic research and development, the AURORA project places Polaris Spaceplanes at the forefront of this critical field. The dual applications of the AURORA vehicle highlight its significance not only for defense but also for advancing scientific research, particularly in aerodynamics and propulsion. Conclusion. In summary, the strategic leap represented by the BAAINBw contract positions Polaris Spaceplanes to play a pivotal role in the future of hypersonic research and development. The AURORA project stands to push the boundaries of aerospace technology, fulfilling essential defense roles while also paving the way for innovative scientific exploration. As the project unfolds, it will be closely watched by both military and civilian sectors for its contributions to hypersonic flight and space access. Additional insights from sources. Source 1: The European Spaceflight article emphasizes the importance of the BAAINBw contract as a significant step for Polaris, which builds on its previous successes with smaller demonstrators. The details surrounding the contract's scope and its potential for future manufacturing and flight testing are crucial for understanding the broader implications of this development. Source 2: Defense Industry Europe's coverage highlights the aspirations for the vehicle to function as a comprehensive testbed for high-speed flight research, reinforcing the vehicle's dual-use nature for both defense and scientific endeavors. Source 3: The next web article provides context regarding the founding of Polaris and its journey through the development of its demonstrators. It also outlines the historical challenges associated with aerospike engines, situating Polaris's innovations within a broader narrative of aerospace development. This contract and the ensuing development of the AURORA vehicle could reshape the landscape of hypersonic flight and its applications, marking a notable chapter in Germany's aerospace ambitions. Counterintuitive information. 1. Cost efficiency versus high-tech development. The announcement of Polaris Spaceplanes developing a hypersonic vehicle under a €50 million defense contract may seem like a substantial investment in high-tech aerospace technology. However, the potential of the AURORA spaceplane to operate as both an aircraft and a rocket could actually lead to cost savings in the long run. This dual capability may make it more cost-effective for launching payloads into space compared to traditional rockets, which often require single-use components and extensive infrastructure. It challenges the common perception that high-tech solutions must be exorbitantly expensive. 2. Military applications coupled with scientific research. Typically, projects under defense contracts are viewed as primarily military-focused with little overlap into civilian applications. However, the AURORA project is explicitly designed to serve both defense-related purposes and scientific research. This highlights the increasingly interconnected nature of military and civilian aerospace efforts, suggesting a shift in how defense projects can also contribute to broader scientific advancements, which is contrary to the traditional notion of a strict divide between military and civilian aerospace endeavors. 3. Historical context of aerospike engines. While aerospike engines have historically faced challenges and have not been widely adopted, Polaris's success in implementing this technology with advanced cooling techniques indicates a significant leap forward. The counterintuitive aspect here is that what has been deemed too complex for mainstream applications in the past may now become feasible due to innovations in materials and engineering. This implies that historical limitations can be overcome with modern advancements, suggesting a cyclical nature of technological progression rather than a linear path. 4. The role of previous failures. The developmental history of Polaris spaceplanes includes initial failures such as the crash of the first MIRA prototype. While failures in aerospace endeavors usually lead to skepticism regarding a company's capabilities, Polaris's continued development and eventual success with subsequent prototypes demonstrate that initial setbacks can provide valuable learning experiences. This counters the common belief that failure in early stages is a definitive indicator of future project failure. 5. Timeframe for development. The 3-year timeline for the design, manufacture, and flight testing of the AURORA spaceplane might seem overly ambitious given the complexities of hypersonic technology. However, the contract also includes options for follow-on initiatives, which suggests a phased approach that might allow for more iterative development rather than a single large-scale rollout. This contrasts with the usual perception that such advanced technologies require extensive timeframes and larger upfront investments to develop successfully. 6. Public perception of defense spending. The announcement comes at a time when there are discussions about increasing defense spending in Europe, especially in light of changing geopolitical dynamics. While public sentiment often leans toward skepticism regarding military expenditures, this project's focus on dual-use technology may actually garner support by framing defense spending as a vehicle for scientific advancement and economic growth, challenging the typical narrative that equates defense budgets solely with military escalation. 7. Reusable technology in aerospace. The AURORA vehicle's design focuses on reusability akin to commercial airliners, which counters the traditional view that space launch systems must rely on single-use rockets. This innovative approach to aerospace technology may revolutionize access to space by making it more economically viable, contradicting the long-held belief that space travel must remain prohibitively expensive due to the nature of current launch systems. 8. Integration of various technologies. The integration of aerospike engines and horizontal takeoff capabilities in one vehicle is ambitious and suggests a convergence of technologies that have previously been developed separately. This counterintuitive blending of technologies indicates a future where multidisciplinary approaches in engineering may lead to breakthroughs that were not previously considered feasible or practical. 9. Role of startups in aerospace. The success of Polaris Spaceplanes, a relatively young startup, in securing a significant defense contract may challenge the conventional wisdom that only established aerospace giants can undertake such large-scale and technologically complex projects. This points to a potential shift in the aerospace industry where startups can innovate rapidly and effectively, leveraging new technologies and agile methodologies that larger organizations may struggle to adopt. These counterintuitive insights highlight the evolving landscape of aerospace technology defense applications and the interplay between military and civilian research, suggesting a future that embraces innovation and cross-disciplinary collaboration. The contract awarded to Polaris Spaceplanes by Germany's BAAINBw for the development of the AURORA hypersonic spaceplane is a pivotal moment in aerospace and defense technology, yet several nuances within the report may be overlooked by the general public. Below I identify these critical elements and explain their significance. 1. Dual purpose of the AURORA spaceplane. While the contract emphasizes the vehicle's roles in both defense and scientific research, many might underestimate the strategic implications of this duality. The AURORA's design allows it to function as a hypersonic testbed and a potential small satellite launcher. This capability reflects a broader trend in military and aerospace sectors towards multi-role platforms that offer versatility in mission profiles. Significance: the ability to serve dual purposes can lead to cost savings and increased operational efficiency. In times of budget constraints, as seen in defense spending discussions across Europe, platforms that can meet multiple needs without requiring separate funding streams for different capabilities are invaluable. 2. Advanced aerospike engine technology. The AURORA project includes the use of advanced aerospike rocket engines, a technology that has historically faced engineering hurdles. The report notes Polaris's efforts to overcome cooling and construction challenges associated with aerospikes. Significance: success in developing reliable aerospike engines could revolutionize propulsion technology, offering better performance across various altitudes compared to traditional rocket engines. This would not only enhance the AURORA's capabilities but could also influence future aerospace vehicle designs, making hypersonic flight more feasible and efficient. 3. Historical context of Polaris's development. The report mentions Polaris's origins as a spin-off from the German Aerospace Center DLR and highlights its development of smaller demonstrators, MIRA II and MIRA III. The previous failures and successes of these prototypes are crucial to understanding the current project's viability. Significance: the journey of Polaris from its inception to this major contract showcases the iterative nature of aerospace innovation. Understanding that Polaris has learned from past failures can instill confidence in the feasibility of AURORA. Moreover, it emphasizes the importance of resilience and adaptation in high-tech development fields, which is often overlooked in favor of only discussing final outcomes. 4. Strategic defense implications for Germany. The contract is part of a larger narrative concerning Germany's military modernization and increased defense spending in response to global security challenges. The report subtly alludes to this context without fully exploring its implications. Significance: the move to enhance hypersonic capabilities highlights Germany's strategic shift toward a more autonomous defense posture within NATO and the EU framework. As NATO dynamics evolve, nations are seeking to bolster their defense capabilities independently, which could lead to a new arms race in hypersonic technologies. This is a critical point that extends beyond the technological development of AURORA. It speaks to geopolitical stability in Europe. 5. Future prospects and commercial applications. The potential of AURORA to serve commercial purposes as a small satellite launch system when equipped with an expendable upper stage is an aspect that might not receive adequate attention. Significance: this commercial viability indicates that government-funded projects can lead to profitable ventures in the private sector. As the space industry increasingly trends towards privatization and public-private partnerships, the dual-use nature of AURORA could pave the way for future collaborations between military and commercial aerospace sectors, fostering innovation and reducing costs for satellite launches. 6. Innovative cooling technologies. The report notes that Polaris is working on innovative cooling technologies to manage the challenges associated with aerospike engines. This detail, while technical, has far-reaching implications. Significance: effective thermal management is critical in aerospace engineering, particularly at hypersonic speeds. If Polaris successfully develops new cooling solutions, it could lead to breakthroughs applicable in various high-performance aerospace applications beyond just their own vehicle. This innovation could subsequently influence other sectors, including commercial aviation and space exploration. 7. Timeline and milestones. The 3-year timeline for the completion of the AURORA design phase is mentioned, but the potential challenges and implications of such a timeline are less explored. Significance: the ambitious timeline reflects both the urgency of the current geopolitical climate and the pressure on Polaris to deliver. Meeting such deadlines is often fraught with risk, and any delays could have significant repercussions, including budgetary impacts, shifts in strategic priorities, and challenges in maintaining stakeholder confidence. This underscores the high-stakes nature of defense contracting and the innovative pressures faced by small startups in a competitive landscape. Conclusion: the developments surrounding Polaris Spaceplanes and their AURORA hypersonic research vehicle represent a convergence of technological innovation, strategic military considerations, and potential commercial applications. The overlooked details in the narrative, such as the dual-purpose functionality, advanced propulsion technologies, historical context, and the implications for Germany's defense strategy, are critical for understanding not just the project itself but also its broader impact on aerospace defense and commercial industries. These elements highlight the interconnectedness of technological advancements and geopolitical realities, urging stakeholders to consider the wider ramifications of such developments. 1. Development of the AURORA vehicle. Polaris Spaceplanes has embarked on a groundbreaking project to develop the AURORA, a fully reusable hypersonic research vehicle. This vehicle, measuring approximately 28 meters in length, aims to operate as both an aircraft and a rocket capable of horizontal takeoff and landing. The AURORA's design includes advanced aerospike rocket engines, which have historically faced engineering challenges but offer significant efficiency benefits at varying altitudes. The vehicle is expected to serve as a testbed for hypersonic flight aerodynamics and propulsion technology, positioning Polaris at the forefront of aerospace innovation. 2. Strategic implications of the BAAINBw contract. The €50 million contract from Germany's Federal Office of Bundeswehr Equipment, Information Technology and In-Service Support (BAAINBw) underscores Germany's commitment to advancing its hypersonic capabilities and defense spending. This contract not only highlights the strategic importance of hypersonic technologies in modern military applications but also reflects Germany's broader defense objectives amidst evolving geopolitical landscapes. The dual-purpose nature of the AURORA vehicle, serving both defense and scientific research, demonstrates a strategic alignment of military and civilian aerospace interests. 3. Technological innovations and past achievements. the development of the AURORA vehicle builds on Polaris Spaceplanes' previous successes with smaller demonstrators, namely MIRA II and MIRA III, which have collectively completed over 100 test flights. These demonstrators employed advanced cooling technologies and materials to overcome the challenges associated with aerospike engines. The historical context of the company's trajectory, including its founding as a spin-off from the German Aerospace Center DLR, provides a robust foundation for the ambitious AURORA project. This lineage of innovation positions Polaris to tackle the complexities of hypersonic flight. For future prospects and commercial applications, the AURORA vehicle is expected to be completed within 3 years, with potential applications extending beyond military uses to include commercial space ventures. The design allows for an expendable upper stage, enabling AURORA to function as a small satellite launch system. This capability not only enhances the vehicle's utility but also opens avenues for commercial partnerships, contributing to Europe's competitiveness in the global space industry. The dual-use nature of AURORA as both a research platform and a launch system illustrates the growing intersection of defense aerospace research and commercial opportunities in hypersonic technologies. 1. The X-15 program 1959–1968. The X-15 was a rocket-powered aircraft that was part of a joint program by NASA and the U.S. Air Force. It aimed to explore hypersonic flight and space travel, reaching speeds of up to Mach 6.7 and altitudes over 350,000 feet. The X-15 program contributed significantly to our understanding of aerodynamics, high-speed flight, and the challenges of space travel. The data and experience gained from the X-15 informed the design of future spacecraft and hypersonic vehicles, making it one of the most significant aerospace projects in history. 2. The Space Shuttle Program 1981–2011. NASA's Space Shuttle program was a groundbreaking initiative that facilitated reusable space travel. The shuttle was designed to carry astronauts and cargo to and from low Earth orbit with the ability to land like a conventional airplane. It showcased advanced aerospace technologies, including solid rocket boosters and a unique thermal protection system to withstand re-entry temperatures. The program produced significant advancements in aerodynamics and materials science, impacting both military and civilian aerospace applications. 3. The Concorde 1969–2003. The Concorde was a turbojet-powered supersonic passenger airliner that operated for over 3 decades. It was a joint venture between British and French aerospace companies and was capable of flying at speeds of over Mach 2. The development of the Concorde involved extensive research into aerodynamics, materials, and propulsion systems. Although it was primarily a commercial aircraft, its technological innovations in supersonic travel contributed to the broader field of high-speed flight and influenced future aerospace designs. Future outlook: Polaris Spaceplanes and Hypersonic Transport Solutions. The recent contract awarded to Polaris Spaceplanes for the development of the AURORA hypersonic research vehicle marks a pivotal moment in aerospace technology and military capabilities. As we look to the future, several predictions can be made regarding the trajectory of Polaris hypersonic transport technology and its broader implications on defense and aerospace sectors. 1. Accelerated development of hypersonic technologies. The 3-year timeline set for the design and production of the AURORA vehicle indicates a rapid pace of innovation in the hypersonic sector. Given Polaris's previous successes with the MIRA series and its advancements in aerospike engine technology, we can expect increased investment as hypersonic technology demonstrates its potential for both military and civilian applications. Additional funding from government and private sectors is likely to follow. This could catalyze a new wave of startups and established aerospace companies to invest in hypersonic research. Technological breakthroughs. The challenges associated with hypersonic flight, particularly in propulsion and thermal management, will likely spur significant advancements. Innovations in materials science, cooling technologies, and propulsion systems could emerge, potentially leading to safer and more efficient hypersonic vehicles. 2. Dual-use applications transforming aerospace. The AURORA's potential as both a hypersonic transport and a small satellite launch system highlights a growing trend in dual-use technologies. The implications of this are profound. Commercial viability. As Polaris successfully demonstrates the AURORA's capabilities, commercial entities may adopt similar hypersonic technologies for faster air travel and efficient satellite launches. This could lead to a new era of aerospace services, where hypersonic flights significantly reduce travel time across the globe. Market competition. Other nations and private companies may accelerate their own hypersonic projects in response to Polaris's advancements, leading to a competitive landscape. This rivalry could foster innovation but also raise concerns about regulatory frameworks and safety measures. 3. Strengthening defense capabilities in Europe. Germany's investment in hypersonic technology through Polaris reflects a broader commitment to enhancing national defense capabilities. Enhanced military readiness. As AURORA becomes operational, it is likely to provide the Bundeswehr with a critical edge in reconnaissance, rapid response, and payload delivery capabilities. This could lead to a reconfiguration of military strategies across Europe with a focus on integrating hypersonic systems into existing defense frameworks. Collaborative defense initiatives. As European nations recognize the strategic importance of hypersonic technologies, collaborative defense programs may emerge. Joint ventures among NATO allies could streamline development processes, share research costs, and enhance interoperability of hypersonic systems. 4. Environmental and regulatory challenges. While the technological advancements will be significant, they will also come with challenges. Environmental concerns. The development of hypersonic vehicles raises questions about their environmental impact, particularly regarding emissions at high speeds. As public awareness of climate change grows, Polaris and similar companies will need to prioritize sustainable practices and seek eco-friendly alternatives in propulsion and materials. Regulatory frameworks. The advent of hypersonic transport will necessitate new regulatory frameworks to ensure safety, airspace management, and international compliance. Policymakers will need to address these issues proactively to facilitate the integration of hypersonic vehicles into global air transportation networks. 5. Cultural and societal implications. The introduction of hypersonic travel could also have cultural and societal ramifications. Changing perceptions of travel. As hypersonic travel becomes a reality, public perceptions of distance and travel time may shift dramatically. This could lead to changes in business practices, tourism, and the global economy as travel becomes faster and more efficient. Education and workforce development. The complexity of hypersonic technologies will necessitate a skilled workforce. Educational institutions may need to adapt curricula to prepare the next generation of engineers and scientists capable of contributing to this burgeoning field. Conclusion. The future of hypersonic transport, spearheaded by Polaris Spaceplanes and the AURORA project, is poised for remarkable developments. As the technology matures, it will reshape not just the aerospace landscape but also global defense strategies, commercial opportunities, and societal norms. Policymakers, businesses, and educational institutions will need to collaborate and adapt to ensure that the evolution of hypersonic technologies benefits society as a whole while addressing the accompanying challenges.